All right, everyone. Want to just run through some quick power analyses with GPower, similar to stuff using some of the examples that we had touched on briefly in class, or we didn't touch on them, but I presented them. If you see over here, we had that slide in the power lecture that had these as examples. What I would just want to do is run through each one of these examples, show you how we would use GPower to go through and calculate power for each one of these, and then maybe show you some other ways, things to think about in terms of when you're calculating effect sizes and things along those lines. So here is GPower. You'll want to download this, have this going on your own computer so you can run through this stuff. Upload or sort of open up the program, and this is the format you're going to see when you first open it up. Now, as we're going through, we're looking at calculating power for various different types of t-tests. So when you go over and you're setting up GPower, first thing you need to do is make sure that you're on the right test. So for us, test family, we're going to be looking at some t-tests. So again, just make sure that you go down through and you click t-tests. Now, once you get the t-test, there's lots of things we use t-tests for. You want to go through and make sure that the analyses that you want to power is the one that you've got set up. So what we're going to do for our first analysis is this single sample case, right? So if we go down through, we want to look at means. So we've got a mean difference from one constant, a single sample case. So right here, so we say means different from constant, one sample case. This is our single sample t-test. So we're going to click that. Okay, and then the type of power analyses. You have some options here. We're going to leave this where it is at a priori. We want to know the sample size that we need to have an adequately powered test based on some information that we have from the existing literature. So we're going to keep this at a priori power, but just to show you, we have some different options, things that you might look at post hoc, although we talked about some problems with post hoc power, but you could calculate post hoc power, look at the power that you've achieved given a sample size, alpha level, and an effect size. We can also look at sensitivity analyses, look at the required effect size we would need given alpha, power, and a sample size. So if we wanted to say, I am able to collect 100 participants. So with 100 participants at 80% power, what is the effect size that I would need to have in order to sort of be adequately powered? So some different things we can play around with that, but for this demonstration, again, make sure that you're an a priori power. Okay. So once we get down to a priori power, we're going to hold on for that in just a minute. So if we look over here on our power calculations, this is just a slide from our lecture. Again, we've got an example for our single sample t, our independent sample t, and our paired sample t. And we're going to run through each one of these individually. Okay. So for our single sample test, what we've got in this situation, we've got scores from an interview measure of PTSD, the CAPS. And what we want to know is we think that there's a difference between scores in first responders relative to people who are actually in car accidents and taking a look at that sample. And so what we're doing here is we want to test whether or not our sample of first responders have lower PTSD scores relative to some known reference score among survivors of motor vehicle accidents. So again, if we go down through, based on, say, previous literature that we found that average CAPS score among first responders has a mean of 65.3 and a standard deviation of 13.5. What we want to know is whether or not this is systematically lower, because we have, maybe our hypothesis is that first responders are generally more resilient. This is why they've elected to be first responders. We're saying that trauma scores or PTSD scores in this group, we're expecting it to be lower than some reference group of individuals who are in motor vehicle accidents. So motor vehicle, our reference number for our motor vehicle accident group is a CAPS score of 70.1, and based on previous literature, we find that first responder scores range somewhere between 65.3 with a standard deviation of 13.5. What we want to know is we want to run a study. how large of a sample do we need in order to capture this effect here. Okay, so what we're going to do is, with our reference material here, go back over to GPower. Okay, and so once we've got a t-test, we say we've got a single sample case. We're looking at a priori power. We need to calculate the required sample size to achieve adequate power to detect the effect that we see in this study. So first thing you're going to do on input parameters, you're going to go to tail. We always want a two-tailed test. Okay, effect size D, we're not going to worry about that quite yet. Our alpha level, we're going to set that to 0.05, and then power. GPower sets your power that you're looking for at 0.95. Again, that's a little high for what we would typically see in psychological science, and so we're just going to set that at 0.80. Okay, so we've got alpha at 0.05, power at 0.80, a two-tailed test, and now what we need to do is we need to calculate our effect size. Now, if you know your effect size, you can just type it into there and be done with it. However, GPower makes it easy. We can go through and we can hit determine. Hit determine, and it just kicks out a little table right here. And what we can do is then calculate our effect size and a measure of effect size within GPower. So our mean value under our null hypothesis, this is going to be our reference value of 70.1. So here we're going to type in 70.1. Our mean under our alternative hypotheses, this is our mean for our first responders based on previous studies, based on previous research. We expect a mean of 65.3 in that group, okay? And then our standard deviation. Now, because we're using a single sample t-test, we know that we don't know, we don't have an estimate of the variance in the population. Now we've got one in this example, but we wouldn't use that. What we would do is we'd go through and insert the standard deviation from our previous study of first responders. So we're going to set standard deviation at 13.5. Okay, so we've got our information in there. Then all we're going to do is we're going to go hit calculate, and it calculates an effect size of 0.356. Okay, so we've got our effect size. We can hit calculate and transfer to main window, push that over, and it pops up our effect size that we've calculated in GPower right here. Okay, so now we've got everything we need. We were looking at a two-tailed test. We're looking at a single sample test, a priori power, looking at a two-tailed test. We've got an effect size, small effect of 0.356. We've got alpha of 0.05 and our power of 0.80. Okay, and so now what we're going to do is we're going to go down and we're going to hit calculate. And based on this information, GPower is telling us that we need a total sample of 65. If we have a sample of 65 people, we're adequately powered. Our actual power is just a little over 0.80, about 0.81. But with 65 people, we are adequately powered to detect an effect size of 0.356 at an alpha level of 0.05 using this single-tailed test. Okay, so pretty easy, pretty straightforward. Now if we go over here, what we can also do is just to double check anytime you're having a program calculate effect sizes or anything like that. I always like to double check it. And so here, if we go down through and we actually calculate an effect size like we would by hand, as we've talked about in class, if we just take our value of, and it's not letting that cursor come up on that thing, but if we take, with our normal D, we take 65.3 minus our reference value of 70.1, divide that by the standard deviation of our first responder group, gives us an effect size that we just calculate a D of negative 0.356, the same effect size that we get here. So everything's squared. GPower is calculating everything as we would expect. Okay, so again, for an effect of this size in a single sample test, we would need a sample of 65 in order to have an adequately powered analysis. Okay. So going over to our independent sample test. Okay, here what we're looking at is we've got a study looking at gender differences in marital satisfaction following disaster among a group of Hispanic individuals. Okay, and what we want to know is maybe we think that there are cultural differences, and we want to replicate these analyses with maybe along with some other stuff, but we want to get a sense for how many people will we need in order to detect the effect that's known in this published study. So in GPower, what we're going to do is we're going to go over, and so we're still looking at a t-test this time, but we're going to go down through and we're going to choose means difference between two independent means, a two-group test. Okay, and so here we're going to keep our a priori power the same. Our effect size we're not going to worry about quite yet. Make sure that we're looking at a two-tailed test. Effect size, we'll calculate that in GPower. Alpha 0.05, and then make sure that we're powering things for power of 0.80. Okay, and so then let's go through and hit determine and let GPower calculate our effect size. So a couple of different ways you can do this. One, if we thought the standard deviation within each group was equal, we could go up here and we could say, all right, here's the mean of group 1, the mean of group 2, and here is their shared standard deviation. Okay. However, we've got means and standard deviations for both groups, so maybe we're going to go down through and we'll calculate it here. Okay. So we've got mean of group 1. Right, so our mean for our women is 108.9. Our mean for our men, 80.2. Standard deviation for our women is 24.4. And our standard deviation for our men is 30.4. Okay. And so based on just plugging in the information that we have from this existing study, again, why it's so important to include means and standard deviations, go through and plug this in, and we can calculate an effect size. It gives us an effect size of 1.041. Transfer this over to the main window, and so go through to just a double check. So we've got a two-tailed test, our effect size that we've just calculated, 1.04, alpha of 0.05, power 0.80, and then we've got this business of allocation ratio. This is looking at discrepancies in sample sizes. So do I have more men in my sample versus women in my sample? For right now, we're going to say that this ratio is equal to 1, which would indicate equal numbers of men and women across both of our samples. Okay, so if we go down through and we calculate, what GPower is telling us is that for an effect, to detect an effect, a very large effect, right, over a full standard deviation difference between our two population means, we see that we would need to pull a sample of 16 from our men and 16 women for a total sample size of 32 to adequately power our test to detect an effect size of 1.04. Okay. Our actual power is a little bit above that, but with 16 people in each group, if we have equal sample sizes, this is what we're looking at in order to drive an adequately powered test. Okay. Now, if you're going through and you're taking a look at this, you might say, well, in our original study, we didn't have the same number of people. We only had 5 men and 21 women, right? And so if we go down through and we think about this, we actually don't have an allocation ratio of 1. We actually have a 4-to-1 ratio. We have 4 times as many women as we do men, right? And so let's just see if we go through and account for this unbalanced design. Let's say that for our study, we expect to get about 4 times as many women as we can men, right? And maybe this is a practical limitation. You just know that you're going to get more women than men, and so something that you need to take into account. So again, before we do this, let's just set this to 1 and hit calculate. So again, with equal samples, we need 32 people, 16 men, 16 women, to get an adequately powered test. Okay, but if we take into account this unbalanced design, and we're saying that we're going to have 4 times as many people in one group as the other, right? And then we go through and calculate, all of a sudden, instead of needing 16 and 16 needing 32 people, we need a total of 48 people, right? We're going to have 10 men and 38 women, so we're going to need a total of 48 people in order to get an adequately powered test. Now, the only thing that's differed here is sort of the balance of our design. Again, really important, really beneficial to try and have a balanced design whenever you can, because you'll notice that as soon as we get this design that's no longer balanced, what we end up needing more people in order to have it achieve an adequately powered test to detect this effect here than we would have if we would have had just a balanced design in equal groups. Okay, so something to be aware of, something to keep in mind as you're running through these analyses, thinking about, for my study, am I going to be able to get equal numbers of people in both groups? If I am, great, but if I'm not, as soon as I have balanced designs, that's going to negatively impact my, or imbalanced designs, that's going to negatively impact my power. Okay. And so one of the things you may be thinking of is, well, okay, this is fine. We went through and calculated our effect size here, but we didn't take into account that we had 4 times as many women as we did men here. And that's kind of problematic, right? Because if we go down through and in this case, we would normally calculate a Hedges G, right? Something that takes into account differences in variability across my samples, differences in sample sizes across my cells. And so if we go through, I've worked this out here, if we calculate a pooled variance estimate for our men and our women, right? So we've got 4 people in the male group times 30.4, because we're working with variances here, we square that, plus 21 minus 1 degrees of freedom for our women, times the square of our standard deviation to get variance here, all divided by 21 plus 5 minus 2, our degrees of freedom. We end up getting a pooled variance of 650.16. We take the square root of that, and we get a standard deviation of 25.498. So if we then take the mean of the women, subtract the mean of the men, divide it by our pooled standard deviation, we actually get a different effect size than what was calculated here in GPower. Okay, we actually get an effect size that's a little bit bigger, right? And so if we go through and we now type this in, right, 1.126 is our estimate of effect, right, with alpha 0.05, power equal 0.08, and we're still taking into account the fact that for this study, we're expecting to get about 4 times as many women as we are men, and we go through and calculate. We get a little bit different estimate for our power here, right? We got a bigger effect size, so we need a slightly smaller sample than what we had estimated previously. Okay. We can also go through and see what happens if we go down through and we go up here. So we had talked about here, if we're using a common variance within each group to calculate our effect size, what we can do is if we go through and we type in 108.2 and 30.4, or excuse me, 80.2, so we've got our mean for our women, our mean satisfaction for our men, and then let's plug in our estimate, our pooled standard deviation estimate. If we type in the pooled standard deviation estimate here, 25.498, okay, and then we go down, we hit calculate, it's given us a slightly different estimate than what we had here. Would need to go through and see exactly how GPower is calculating this effect here within each group. Not sure, would need to go through and take a look, but just to show you some different ways of going through and doing things. In general, though, probably the best option is going to be going through and calculating your effect sizes by hand and then plugging these in, just because then you know sort of the type of effect that you're going to need. Other thing for this situation, now if you're taking a look at this, you'll notice that we have small samples here. A sample of 21 is pretty small, a sample of 5 is very small, and so maybe instead of calculating a G statistic or a G effect, maybe you say, well, I want to make a correction for potential upward bias, and so what I do here is maybe I take my G and multiply it by my correction factor for an Hedges unbiased G, and what I end up with is an effect size of 1.090. And so here, maybe I want a more conservative estimate. I say, okay, so I'm afraid that my just my estimate of hedges G is going to be an overestimate of the true population effect. Because I do have small samples, I'm going to calculate hedges unbiased G as a correction, and I'm going to put that in with alpha equal 0.05, power equal 0.80, an unbalanced design, 4-to-1 difference between men and women in terms of my sample size, and calculate. And now I get a little bit different answer here, right? So I've got it's telling me I'm going to need 9 men, 35 women for a total sample of 44 to have an adequately powered independent sample t-test with power 0.81. Okay. And so finally, taking a look at our paired sample tests. Here, we're looking at detecting pre to post change in interpersonal functioning following some sort of inpatient treatment. Okay, so our baseline, we got our 19 people. We got 19 people because this is a paired sample test. We have to have the same number of people. We have a score of sort of 4.3 in this distant interpersonal style. So these are people who are isolating themselves and not getting along with people. And so their score on this measure to start is 4.3 with a standard deviation of 3.6. By the time they finish up treatment, their scores have dropped down to 2.6 with a standard deviation of 3.7. And the intercorrelation between these two measures is 0.78. Okay? And so what we want to do is, this is something that's been found in the existing literature. We want to see how many people do we need in our sample in order to detect this effect at adequate power. So again, we're still using a t-test. We're going to go to means, and we're going to go to matched pairs, right? So this is the difference between two dependent means. This is our matched or a paired sample t-test. Going to select that. Our a priori power, we're still looking at a priori power. On a two-tailed test. Effect size, we won't worry about that quite yet. Our alpha is 0.05, and our power, change that back over to 0.80. Okay, we'll determine our effect size. Asking for the mean of group 1. So the mean of group 1 is going to be, or at time 1, 4.3. Mean at the time 2 post-treatment, 2.6. Standard deviation at time 1, 3.6. Standard deviation at time 2, 3.7. And then the correlation between groups. This is important. This is what gives us our power for our repeated measures design. We're going to have a correlation of 0.78 between these two measures. So scores at pre-treatment, scores at post-treatment correlated 0.78 with one another. Okay, and so if we go down through and we calculate our effect size, it gives us an effect of 0.70. Calculate and transfer this over. So we've got an effect size of 0.70, alpha level 0.05, power 0.80. Calculate, and for this effect that's approaching standards for a large effect, we would only need a total of 18 people in this sample pre-post to have an adequately powered test at power equal 0.80. Okay, and so here, if we go back over and take a look, again, we could also calculate mean from the differences here, mean of the difference over standard deviation of the difference. One way you can go through and take a look, but generally what you're going to want to do when you can is go through and take a look and include that correlation factor in there. And if we go through, and if you remember that by hand, when we're calculating our effect size for our power analysis of a paired sample test, we calculate D a little bit differently. We still here have mean 1 minus 2, so we've got our different score here, but in the denominator what we've got is this variance of x1, or standard deviation of x1 minus x2. And if you recall, we calculated this as our standard deviation estimate multiplied by the square root of 2 times 1 minus rho. This is 2 times 1 minus the correlation between our two measures. And if we do that, this is what we end up getting. Our average variance, again, important. Remember that when we're averaging, we're always working with starting with a variance and then we're going back through and grabbing our standard deviation after we've averaged the variance. the average of the squared average of your variance isn't going to be the same thing as the average of your standard deviations, not the same figure. Always want to make sure that you're starting with your variances. But if we do this and we go through and we take 3.6 and square that, plus 3.7, square that, divide it by 2, we get an average variance of 13.325. Take the square root of that, gives us an average standard deviation of 3.65. Okay, and so then to get our standard deviation of x1 minus x2 for the purpose of calculating power, we would take 3.65, multiply this by the square root of 2 times 1 minus the correlation between our measures, which is 0.78. Multiply that out. We get a variance or a standard deviation estimate of 2.421. And then if we go through and we use this in the calculated version of our effect, specifically for the purposes of calculating power, this isn't an interpretable effect size that you would report, but for the purposes of calculating power, this is how we need to do it. And so if we take our pre-treatment minus our post-treatment divided by 2.421, which is the standard deviation measure that we've calculated for the purposes of power, we get an effect of 0.703, okay, which is very, very similar to what GPower is calculated based on this. Okay, and so again, if we go through and we just enter what we've calculated, 0.703 at alpha equal 0.05, at power equal 0.80, we get functionally the same answer, right? We just tweak that very small, very little. Okay. So hopefully this gives you a sense for what's going on, how to go through, use GPower in general for your analyses, for your assignments. You guys know how to calculate effect sizes. Calculate your effect sizes by hand and then just go ahead and plug those in. But then also go through and use this as a double check. You should get for your effects something that end up being close between what you plug in here and what you get from GPower. So just go through and be mindful of that. One last thing that I would show you, just as a preview, a heads up, with some of this stuff. As part of this assignment, you are going to be creating effect size calculators similar to the one I have here. This is really slick. This makes your life very, very easy. Okay, so for example, let's go back to the top here, and let's say that I want to calculate my effect size for this test. So I want to calculate an effect for this single sample test. In my calculator, what I can do is I can go through and type in the mean for my first sample is a mean of 65.3. Mean of my second, my reference group is 70.1. My variance, now here I have standard deviation, but I can quickly take 13.5, and I'm getting that from my standard deviation of my first responder group, and I can take the square of that. It gives me a variance of 182.25. Go down through, and I have my effect size of 0.3556. Now I've got some other stuff going on where I can enter NCPs to get the confidence interval for my effect size. I'll follow up with that in a different video. But for the purposes of just calculating my effect size, boom, there it is. And again, if we go down through, we'll see that this is exactly precisely what I had gotten here. It's just this is done in Excel, so you don't have to round or take anything to round off any decimal places or things along those lines. So it's nice to be able to have this in, and so you can do it slick once you have it set up. Very easy to go through and calculate these things. Same thing if I go to want to calculate my hedges G, right? I've got it calculated here for independent samples with my pooled variance. If I type in my satisfaction for women 108.9, my satisfaction for my men 80.2, standard deviation for the women is 24.4, standard deviation for the men 30.4. Okay, this is calculating. I have this calculating my variance for me, so I don't even need to fool around with that. Sample size for my men is 5, women 21. Go down through, and take a look at my effect size that I found for my G. My G is 1.126. And now, so this is, did I make a mistake there? Well, let me go back through. I need to investigate what's going on. I suspect that my hand calculations are off somewhere, because this should be good to go. That's embarrassing and not something I want to redo the whole video for, but what we see is, so this has gone through, calculated my hedges G and my hedges unbiased G, have this all set up within the calculator. So ignore the fact that those don't actually work out to what they should be, which is troubling to me. I suspect that I may have calculated my okay, so my pooled variance, my pooled standard deviation here is a little bit different than what it is here. I'll go through and check this out, but you get kind of the picture for what this should be looking like. And then in terms of my paired sample T, same thing. I can go down through and type in 4.3, 2.6 for my other one, standard deviation 3.6, 3.7, correlation is 0.78, and my sample here is 19. Going down through and being able to pull up some effect size. Let's see if did this match up. Yeah, okay. So here is my D paired that I have set up here, similar to what I had got, 702, 703. Looks like I may have made an error in calculation of my pooled variance in this slide, but I will go through and resolve that. But hopefully this gives you a sense for what's going on with GPower, how to go through and use it, basic functioning, and being able to make sure your stuff is set up. So just be careful. Make sure that you're always choosing a two-tailed test. Make sure that you've got an adequate measure of your effect size. Alpha is 0.05, probability is 0.80, and then just make sure that you're on the right test, and you'll be ready to go. So good luck. Let me know if you have any questions, and hopefully this video was helpful.